Sit down. So, welcome back. So, our next speaker will excite you over the lunch coma easily with his very interesting presentation on MACsec and ISO 26262. Steffen Lorenz is a principal system engineer at NXP. In his role, he is responsible for the definition of Ethernet products with focus on physical layer and functional safety. He also participates actively at various Open Alliance working groups. I know Steffen already from the FlexRay Consortium, where he worked on physical layer as well, like me. So, Steffen, floor is yours.
Thank you. Yeah, welcome, and I hope I can make true what Thomas said. So, have an interesting presentation to keep you awake after a very delicious lunch. So I will start with something I will not talk about it, and that's the general question if we need security in our cars. I think that's obvious. So some examples here shown which show that at the end security is a must-have for our cars. So that's not the question to answer, but what will I ask or talk about? MACsec is one of the ingredients that can be used, and so I will briefly discuss about it, but also there I will not questioning it. So it's just to give a bit of the background that is needed to understand the functional safety part. So the main part will be understanding the functional safety for Ethernet, and then specifically functional safety at MACsec. And then of course, finally a summary and conclusion. So let's start with security in automotive and MACsec in specific. You have seen this picture today already in several presentations, so that's where we move as an industry. And you see that with the steps towards the zonal architectures, and if you look to the very right, the software-defined vehicle optimized architecture, you see a lot of high-speed communication, which is most likely Ethernet. And so this is where all the communication runs on. So that those links needs to be protected. And as said, the protection of the internal communication is one part of the overall security in the car. So if we look to this in a bit more detail, you see here this kind of zonal architecture, and you might have links which go from maybe a sensor towards the central processing. This might go via several hops, and there are two possibilities how you can use MACsec. You can use it end-to-end, so which means the complete link from the sensor towards the central compute is protected, or you do it hop by hop. There's also some discussion at the moment, seems to go more to hop by hop, but fortunately for what I try to show you today, that's independent whether it's hop to hop or end to end. So in principle, from the networking security, this is the main part. So it's about authenticity and integrity of the data. So to make sure that the data source is actually what is supposed to be, and to be sure that this is authenticated, and also to make sure that the data was not modified on its way. Another possibility is confidentiality of data. So to make an encryption that is not necessarily needed. So MACsec is providing both, but it can also be just used as an authentication. If we look now a bit more in detail and how MACsec fits into the parse. So you have two nodes, and this can be an end-to-end node. So then you would have a secure channel which also has some bridges in between, or it is just the hop-to-hop portion. So you have a host controller with your MAC actually in, and then you have somehow PHY, and it goes to the secure channel. Now you see that is showing two possibilities. So the MACsec can be in the PHY part. It can also be in the on the MAC sides on the host controller. Which is common in both cases is that the key management, all the configuration that's handled by the host controller, and then the data at a certain point is authenticated and it is sent around. If you look to the portion what is done in MACsec, so 802.1 AE, so first of all, it is blocking all messages which are not MACsec tagged, and there are secure channels which have an authentication to make sure that you just run the data from in this secure association. In principle, what happens there is on the transmit side, there is a MACsec tag added. You see it down here, and the MACsec ether type is added so that the receiver knows about it. And there is also a validation tag, so CSC code in principle, added to this. And if encryption is used, of course, also the payload is encrypted. So now you see there is some modification of the frame. And if the frame is modified, this means also the CSC, so the FCS needs to be recalculated. And that will be one part we are looking at. So yeah, why it is important to make sure it is covered. At the receiving side, it's the other way around. So the first step will be to decrypt the packets. So to recover the original message. And then, of course, check the tag authentication to make sure that it fits to the key which is on the receiver side. And then from there, the sec tag and ICV will be removed so that the original frame will be recovered. So that's on functional, on MACsec. Now a brief overview of functional safety. And if we look to functional safety, we have for automotive the ISO 26262. And in principle, it is trying to quantify the risk and define the system in a way that it behaves in a minimum risk level that is acceptable. The ISO says it is the absence of unreasonable risk due to hazards caused by malfunctions in EE systems. And that's what we try to achieve. And there are the famous ASIL A, B, C, D level, so you might have heard about it. And so what is behind this? Let's take a closer look to this. And this is now very much simplified. But in principle, what is done is you do a analysis on situations the car can be in to see what if some hazard happens, so something goes wrong, what would happen? So what would be the severity of the fault? What would be the exposure and the controllability? And with those inputs on car level, you define what is the what are the requirements on car level. So on car level, we are far away from the Ethernet channel, but at the end, you define this from the top level. You make it, or the system definer makes a safety concept to say, okay, which portion is covered by which part, and this one is also inheriting the safety requirements from the top level, but also the safety goals. Also the ASIL level of this. If we now look specifically to Ethernet as a serial communication, you can find a couple of things that are relevant. So you do not want to have data inserted, you don't want to have frames corrupted or lost. Frame loss is something which happens in the network, but it should not be undetected. You also should not delay, repeat, or change the sequence of messages unless it's planned by priority, for example. And you should not masquerade or incorrect addressing of the information, so that it goes to some way where it's not supposed to be. Now the question is, can we do this always end-to-end? At the end, you see, and that's the first part, the ICs itself, so if you think of a PHY, if you think of a switch, that is only a small portion of the overall chain. So there is somewhere a sending MAC, there are wires in between. So there are a lot of failures which you cannot detect just by a PHY or just by a switch. So therefore, you will need to have a certain end-to-end protection. You need to detect if messages are missing, right? But if we are looking to autonomous driving, if we are looking to cars which are having more functionality and more self-driving capabilities, we also need to look into the availability and need to make sure that we not too often park the car somewhere in a safe state, but the car should keep on going. So for this, we need to make sure that we also have the right features in. And if we look to networking ICs in general, so not everything is valid for PHYs and switches, but in principle, we can try to prevent failures in the first one. So with the right quality, with the right design, we can make sure that a certain failure is not causing the car system to fail. If we have the possibility to predict certain failures, so if we see, okay, there are some issues coming up before it really fails, then we also have the chance to maybe reconfigure the switch, reload the configuration if something is wrong with this. And finally, if a certain failure happens, of course the end-to-end protection will detect it, right? No doubt on this. But if we can detect it on the local level where it happens, we have the chance to react on this. So we can, for example, reconfigure the switch. We can make sure that we're not blocking certain traffic passes for high secure failure. So this is all about features we can implement, but there's one more thing to the functional safety process, and that's the safety process itself. The culture in the companies, how it is defined, how the products are developed, and what is the mindset in defining and creating the products. And with this, you also make sure that you prevent systematic failures, for example, with the right methods of reviewing, and also this plays a role in making sure that you have the right quality and the right availability of your system. So there's one more point. I just briefly want to touch it because I later use this term, and that's a latent fault. And so a latent fault is in principle a failure which is not directly causing an issue, but it is causing the loss of your protection of a failure. So you could think of this like the seatbelt. So if the seatbelt is not closed, it's not an issue, right? Nothing will happen by this. But if the seatbelt is not closed and you have an accident, then you might have or might get more injured than you would have with the seatbelt fastened. So there are quite some metrics behind, which is calculated then on the overall level. But in principle, it is there to make sure that you see if something is not working before it happens. And so you regularly check on those things. So with this, it brings me now to the specific part of functional safety in MACsec. And to start this, what is new with MACsec? We are adding into the data path additionally some logic, and there is some additional processing. And just simply speaking, more complexity also gives a chance of more failures. And so this is what we have to deal with. And what exactly we have to deal with, let's look again into the tasks we are doing. And I've highlighted some here. So in principle, we establish a secure channel and a secure channel identifier. All this depends on the right configuration, right? So if the configuration is wrong, that path would fail, or could fail. Then the second one is on the transmit side, we add the secure tag and the integrity check value. As the content of the frame is changed, as I said earlier, also the FCS gets changed. And with this, there's a chance or risk that you have a wrong FCS to your data. Then, if you go for encryption, of course, the encryption process might fail. And finally, on the receiving side, you want to decrypt the packages, either on the real receiver, if it is end-to-end, or on the switch side, for example, if it is hop-to-hop. And you want to take the data and work with this. In principle, the software, or everybody who is using the data which is coming out, is trusting on the correct decryption and receiving it on the correct secure channel. So that's what we want to get. So now we need to see which failure modes can work against this and what can we do for this. And I clustered this in two groups. And so one is the processing side. So we have some data processing, so it goes through the MACsec block, and at the end, it gets a new FCS connected. So what can go wrong? Of course, it might get out with a wrong FCS, or a corrupted data, which gets a new FCS, which is then correct, but the data is wrong. So one of the safety goals, so which is in principle to say what must not happen, so the frames must not be forwarded with corrupted integrity. And with this, you need to make sure if there's some issue in the processing that no valid FCS gets added to it. Because then you would see on the receiving side, on the other end of the channel, you would get something which has a correct FCS. So the FCS check is correct, but the data itself is wrong. The second thing is the configuration. So in principle, the frames must not be forwarded to incorrect secure channels, which turns down to the configuration. If the configuration is corrupted, you send them in a wrong way. For this, you would need to check your configuration, so make sure that the configuration is correct, and if it is not, you still have the chance to invalidate the FCS. That would make sure that the frame gets dropped. And you also can or should have a latent fault check that regularly checks, for example, after startup, that your configuration is correct and stays correct. So you need to define, depending on the process, on which failure modes can cause a wrong configuration. You might regularly repeat to read the configuration, to check the configuration, to make sure that it stays correct. And this already brings me to the end of my presentation. And yeah, let me summarize what I presented and what we look to. In principle, security is a must-have, especially for software-defined vehicles. And MACsec is one of the ingredients for multi-layer protection. As said, it's not the only one, and there might also be other options, but it's one. If you have such an EE architecture, functional safety is a must-have as well. So we need to deal with this, and you need to define the safety goals, and you might also need some latent fault checks to make sure that your system behaves as defined. And finally, it will help to keep the secure network safe and to increase the availability. So it's not making it more safe than it would be without, but keeping it safe while you add the security. And with this, say thank you for your attention, and I'm open to questions.
So, thank you, Steffen. Very good. Are there some questions? No? Seems not. I have a question now with this perspective, functional safety, security, in conjunction. Where do you think MACsec makes more sense, in the switch or in the PHY, or where should it be located?
In principle, so from the functional safety point of view, I would say it doesn't matter. So you can have it in both. From the security point of view, it's a bit the discussion on what you want to do. If you just want to cover the cable, then it's also independent where you put it. If you want to use encryption as well, and you fear a attack towards your PCB itself, so that someone spies on the MII, then it might help to have it in the Mac, because then the data already gets encrypted. On the other hand, having it in the PHY helps you to easily adapt microcontrollers which do not have MACsec, so you can easily attach it to it. So I think it's not a clear yes or no or pro or con for each solution.
All right, thank you. Further questions? Seeing none? No,
Yep,
there is one.
Anil Dhonde, Ethernovia. In one of your slides, you made a comment about predicting failure. Was that just a FUSA-related comment, or was that in the context of MACsec?
On this slide, that's quite common, or just a general statement what you can do.
Okay.
I think in MACsec there's I have no idea of specifically a prediction of the failure. One could be if you have some checks on your configuration, you might have some means to detect even before the configuration changes that you have some failures, so that you can have a live check, for example, and before it is used the next time, you make sure it is corrected. That would be a kind of prediction or online correction of a configuration, for example.
Okay. Thank you.
Any further question? So then, thank you again, Steffen. Very good contribution.
Thank you.